Alright, in this video I'm going to be giving an overview of the geology of Arizona, in particular of northern Arizona. So here we start with a satellite view of the Earth, and the boundaries are faint, but here's the boundary of Arizona here. Okay. Tucson is located roughly here, Phoenix is here, Flagstaff is here. So we're going to be focusing mostly on this part of the world in this discussion today. So in terms of the geologic time periods that we're covering, I'm going to be starting at roughly 2 billion years ago. So in the beginning part of the Proterozoic, talking a bit about the rocks that are the lowest and oldest in the northern part of Arizona, and marching towards the present, spending a lot of time in particular looking at the Paleozoic and Mesozoic rocks. Now in terms of topography, the shape of the surface, and of the geology that we see, Arizona can be divided into three distinct parts. The Colorado Plateau is the northern half, or third or so, and it's relatively flat compared to the surroundings and elevated. And in the southern half or so is called the Basin and Range Province, which is a bunch of small mountain range, relatively small mountain range, broken up by sedimentary basins or valleys in between. So for example, here's the Catalinas, here's the San Pedro Basin next to it, here's the Catalinas, here's the Tucson Basin on the other side. And in between is what we call the transition zone. It's a mix of topography of Colorado Plateau and Basin and Range. It's also a mix of the rocks you find in the Colorado Plateau and those you find in the Basin and Range. We're going to be focusing most of our time on the Colorado Plateau area. In terms of a shaded relief map, which is what this shows, the boundary of Arizona is roughly here. You can see these three distinct zones fairly well. Here's the Colorado Plateau, relatively flat. Here's the Basin and Range, small mountain ranges separated by basins, and the transition zone, which is the edge of the Colorado Plateau here. So let's start with a geologic map. We've seen this before. Roughly speaking, you can divide Arizona again into three parts. The northern part, which is dominated by Paleozoic sedimentary rocks with a few younger volcanic rocks on top. The southern part, which is dominated by Paleozoic to Mesozoic to even Cenozoic volcanic rocks. And then the transition zone is kind of a mixture of the two. So let's zoom in on this area, the part of northern Arizona we're going to be focusing on today. So here we are. The blue colors represent sedimentary rocks of the Paleozoic, shales, sandstones, limestones. The green colors on this side represents Jurassic and younger terrestrial sedimentary rocks, sandstones and the like that form on continents above sea level. And then the pinks and purples down in oranges down here represent younger tertiary and quaternary volcanic rocks of the San Francisco volcanic field. So our story starts about 2 billion years ago during the formation and breakup of the supercontinent Rodinia. So here is a picture of the sort of breakup phase of Rodinia, but we have to go back in time a little bit to the formation of Rodinia, when more or less all of the world's major continental landmasses were combined into one supercontinent, consisting of Laurentia, which will become North America, pieces of Siberia, Australia, Antarctica is down here as well. All of these continental landmasses were more or less connected and compressed into one supercontinent called Rodinia. So this happened around 2 billion years ago. So this convergence of continental landmasses caused uplift of major mountain ranges. It caused the accretion of terrains onto continents, in particular Laurentia, which grew over time as these terrains were pasted on the side of Laurentia. And in particular, this happened along the southeastern margin, what we today call southeastern margin of Laurentia. These colored zones represent separate terrains and when they were formed, major mountain building events and terrain accretion events. For example, the Mojave province here formed at around 2 billion years ago, the Yavapai around 1.8, the Mazatzal around 1.7, etc. So this accretion of material and formation of new rocks and growth of the continents may have happened something like this. So what this picture represents is a piece of the North American continent, the Wyoming province or the Wyoming Craton. It's a part of the backbone, the core of North America, around 1.7 billion years ago. And so what we had along this margin were potentially multiple subduction zones, which look like this image. And so because each subduction zone causes volcanoes, causes eruptions, causes igneous rocks to form, and these volcanoes get eroded, and as does the material from the continent, it gets eroded and it's dumped in the intervening sea. This region collects lots of sediment, both sediment from the continent and material from these erupted volcanoes. And so because of the nature of plate tectonics, basically the plates on the left are moving to the right, and all this material intervening is getting compressed, and these island arcs are getting pasted on the side of North America. So jump to this picture. So here's again the core of North America. The purple stuff is what was forming in this area. The green stuff is what was forming in this area. So the rocks that formed here, these old rocks which formed around 1.75 to 1.65 billion years ago, are largely metamorphic rocks. They started out as sediments and volcanic material in the ocean in between and the island arcs themselves. But as they got pasted on the side of North America and compressed, they were heavily metamorphosed. And they're largely metamorphic rocks with some igneous intrusions. So the basement, the core bedrock of northern Arizona are these igneous rocks which formed in this manner about 1.75 billion years ago. So if you go down to the bottom of the Grand Canyon, the very bottom rocks in this cross section here, they're metamorphic rocks with some igneous intrusions, and they are highly foliated. And in fact, the foliation you can see here is near vertical. So these rocks, imagine, started out as horizontally layered sandstones and ashfall deposits, but those minerals have been so heavily metamorphosed, the foliation is now 90 degrees. It's now vertical. These rocks are also intruded with this pink igneous material, this granite, which is about the same age but slightly younger. And in some cases, you can see here, this granite itself has been distorted and contorted during the compression and metamorphic phase. Now, the supercontinent didn't stay that way forever. As they do, these supercontinents eventually break up. And what we have here is a depiction of what the breakup may have looked like as these pieces along the western margin of Laurentia moved away and opened an intervening sea. So during and after the breakup of North America, the west coast of Laurentia, the west coast eventually of North America, is what we call a passive margin. And what this means is that this part of the world wasn't very tectonically active. It was relatively low-lying near sea level, and it was a relatively quiet place there, tectonically speaking. And so sediment collected. Erosion of the continent, erosion of the mountain ranges that formed during the collision and formation of Rodinia, all that material is now deposited here following the breakup of Rodinia in this passive margin. Now, it's important to note that Rodinia existed near the equator, and in fact, where the Grand Canyon eventually formed in this corner of Laurentia was south of the equator. But this was near the equator, and meaning the passive margin that formed along the western margin of Laurentia, was collecting sediment, was a warm, shallow sea, ideal conditions for shallow marine sedimentary rocks like limestone, shale, and sandstone. So here's what the western margin of Laurentia may have looked like. Sediment being taken from the continent, dumped into the ocean, and some forming in the ocean, like limestone. Now, here's a picture of the paleogeography of what it may have looked like, of what the continents may have looked like during the formation of Rodinia. So here's kind of peak Rodinia formation, major mountain ranges due to collisions of these continental pieces. This one here shortly is going to move to our left as well. There it goes. But the breakup of Rodinia or the eventual breakup of Rodinia, which is happening right now around 750 million years ago, left the western margin of North America as passive margin. So here's Arizona. Here's where the rocks of Grand Canyon are going to collect. The major rock group of note that formed during this breakup of Rodinia, this late Proterozoic period, is called the Grand Canyon supergroup. And in this cross-section, they're down here, there's these tilted, mostly shallow marine sedimentary layers, shales, sandstone, some limestone. Now, I'm not going to say a ton about these. They are exposed in the eastern part of the Grand Canyon. This is taken from down near Desert View or Lippin Point, probably. And this view is a bit broader view. These rocks are the ones that are dipping off to our right. The dip is exaggerated here in this cross section, but we're dipping off to our right here, gently off to the east. So the thickness of this Grand Canyon supergroup is about twice the thickness of the overlying. So it's hard to tell that when you look at it in this view, because you can only see sort of one or two layers at a time. But the Grand Canyon supergroup rocks are quite thick, 10 to 12,000 feet thick, 2 to 2.5 miles thick of sediments that accumulated on this margin. So the rest of the info on the supergroup is going to come later. All right, so let's jump to the Cambrian. So at the end of the at the end of the Proterozoic, we had the breakup of Rodinia, the formation of the Grand Canyon supergroup, which also eventually got tilted. Now we jump into the beginning of the Paleozoic, that is the Cambrian period. So here we are at the passive margin of North America. Here's the boundary of Arizona. And this is what it looked like. So Grand Canyon is here. So in the early part of the Cambrian, we had a very shallow sea / shoreline, depending on the elevation of the ocean. So this is great conditions for sandstones, shales, and limestones. And that's exactly what we see forming at this time, the bottom of the flat-lying layers in the Grand Canyon, the Paleozoic rocks. These Cambrian ones are the Tapetes, the Bright Angel Shale, and the Muav limestone. Here are these bottom three layers here. The brown one, the gray one, and the green one are the Tapetes, Bright Angel, and Muav limestone, all formed near or at sea level. Jumping forward in time a little bit to the Ordovician, most of Arizona was above sea level at this time, and so there were really no significant rocks deposited, or if they were eroded. Okay, so most of the Ordovician and the Silurian, for that matter, here we are in the Silurian, was above sea level and primarily an erosional environment. And so this created about 150 million year unconformity before the next layers formed. The Cambrian has lots of rocks. The Ordovician and Silurian, there aren't any. It's an erosional surface and unconformity. On top of that, we have these rocks forming in the late Devonian. Late Devonian in the Devonian, and here depicted the late Devonian was a period of sea level high stand. And so this part of Arizona was covered by a shallow sea. Ideal conditions to create a layer of limestone, and that layer here is called the Temple Butte Formation. Now, it's not everywhere in the Grand Canyon, and I'm not going to get in here as to why, but it represents the next layer formed on top of the Muav limestone, in between of which is 150 million year or so unconformity. We jump forward in time to the middle Mississippian. We're still at a period of sea level high and even higher than the Devonian. And so again, this is ideal limestone deposits. And the Mississippi is when one of the probably the most prominent layer in the Grand Canyon, the red wall limestone, formed here during the Mississippian. We jump forward in time to the Pennsylvanian, a period of relative sea level low. So much of Arizona, almost all of Arizona was above sea level. But we had nearby a major mountain range, the ancestral Rocky Mountains, which we've talked about before. So these formed thanks to collision of Gondwana and Laurentia, and pushed up what we call the ancestral Rocky Mountain ranges. And so provided a lot of sediment, which could move in the southwest direction as these mountain ranges were eroded. And it's during this time when the Supai group formed here, which is these four main layers, which sit on top of the red wall limestone. So the Supai groups are sandstones and shales, which are either river deposits, or some of them are also aeolian, meaning wind-blown sand with crossbeds. And so these are definitely terrestrial deposits, which occurred when this part of the world was above sea level. We jump forward in time to the early Permian. This is a period of dryness, of a vast desert which stretched roughly from Wyoming all the way down to southern Arizona. And it was quite dry here and windy. And so this is when the Coconino sandstone formed. Coconino sandstone is full of crossbeds, indicating that it is a deposit of windblown sand in sand dunes. So Sahara-like desert here at the time. Moving forward in time to the early Triassic. So we've moved through the Paleozoic. We're starting here, the Mesozoic, and starting with the early Triassic. The end of the Permian saw one last sea level rise to deposit the Kaibab limestone, the topmost layer at the Grand Canyon. But here forward, Arizona, northern Arizona, is going to be above sea level, and so all the rocks that we see are going to be largely terrestrial, rocks that formed on continents above sea level. So the early Triassic looked something like this. We had a lot of subduction along the western margin of North America, mountain building in southern Arizona and in the rest of western North America too. And so there's a lot of sand and mud being eroded from these mountain ranges and transported in this direction. Furthermore, in the late Triassic, it was a wetter time period, more erosion, more movement of sediment by rivers, generally towards the northeast from the major mountain ranges in the southwest, so sediment moved towards the northeast. And so some deposits that formed in the Triassic are called the Moenkopi and Chinle formations. So these are the last two on this cross-section here. The last two little bits of the Triassic rocks, which used to cover the whole area above the Grand Canyon, but have since been eroded away, except for one spot in the park, which contains the Moenkopi and Chinle. The Moenkopi is a fine-grained sandstone, and the Chinle is a shale. The Chinle comes in a whole variety of colors. It's a really beautiful outcrop. And it also is part of Arizona that contains the petrified forest. These trees were buried by the Chinle Formation, petrified, later eroded away. The Chinle Formation later eroded away. Moving forward in time to the Jurassic, another period of widespread desert environment here, again from Canada all the way to Mexico, Sahara-like desert. And so you can still see that. You can see that at the surface pretty easily. And so this is a satellite view of the Four Corners area. So here's Arizona, Utah, Colorado, New Mexico. And so all of this kind of red and brown area is exposed Mesozoic, most of it Jurassic age, terrestrial sedimentary rocks, mostly sandstone, the most famous of which, and one of the thickest layers, is called the Navajo sandstone. So if we zoom in on this area here, here's what we've got. So here is the Colorado River, this way, flowing into Lake Powell. Here is the San Juan River. And these two are both wider, much more prominent satellite view here, only because the Lake Powell backs up the river all the way this far. So this is basically lake. This is all basically lake all the way this far. One of the tributaries of the Colorado, this one is the Escalante River. And one of the tributaries of the Escalante River, this here is called Coyote Gulch. I tell you that because we're going to go down into Coyote Gulch here in a moment. But all of the red rock that you see here is exposed at the surface, Navajo or similar age Mesozoic sandstone that formed during widespread desert conditions during mid-Jurassic. So this is what the Navajo sandstone looks like on the ground. So this is a famous geologic spot in northern Arizona called the Wave. These lines represent parts of dune deposits that were then eroded and more dunes deposited on top of it, etc. There are a number of arches. This is called Stevens Arch. This one I don't remember the name, but there are a number of arches within the rock layer of the Navajo sandstone, which is this one. Okay, so we're going to take a little virtual trip down into Coyote Gulch. It's again one of the tributaries of the Escalante, and it cuts into the Navajo and the Wingate sandstone, which is just below it. So I'm going to jump out of here, and I'm going to take you on this trip using photospheres, 360-degree photos from the trip that I did A couple of years ago. So this is on a mid-September day, and this is what the landscape looks like out there. It's relatively barren in terms of vegetation because it's quite dry, and this is what it looks like. It's also relatively flat where we are, and we're walking across this exposed sandstone, that's sometimes called slick rock. And eventually, though, we get to the edge of Coyote Gulch, and there's a roughly 1,000-foot cliff. And so looking down, you can see my finger holding the camera, but down there is about a 1,000-foot cliff down into this drainage. And so what we're going to do, there's a way to get down through the rocks. We're going to walk down this big sand dune here, which is this thing in front of me, walk down here in front of this sandstone monolith. I'll show you that in a second. And then down into Coyote Gulch itself down there. What you can see down here in the distance is the Escalante River, which then flows off to the right. You can't really see where it goes. So let's walk down this this sand dune. Here's the monolith I mentioned. Here's Stephen's Arch I showed you a second ago, just to give you a sense of scale of where we came from. Here's the sand dune. The previous picture was taken from roughly there. I'll turn us back around again. We're going to keep hiking down this sand dune right to down there, down into Coyote Gulch. So here we are down in the gulch. There's a stream I'll show you here in a second, so it's pretty well vegetated, lots of nice trees and shade. But you can see these walls of Navajo sandstone are a couple of 100 feet high. I don't know how exactly high, but something like a couple of 100 feet high. Now, the various layers of sedimentary rock here aren't all the same strength. And so as the stream erodes through these rocks and the stream kind of meanders across its path, it sometimes finds weak layers, and it takes a turn and it erodes those weak layers underneath much stronger layers. And so that's what we're standing in here, is one of these cases where the stream, probably in major storms, has eroded this relatively weak layer of sandstone, leaving this overhang of much stronger sandstone. Pretty common feature in rivers that are incising into sedimentary rocks like this. So here's the stream, and there are occasional little waterfalls here. The stream is quite sediment rich. We weren't able to actually drink this. We had to find places where springs to get fresh water. This is drinkable. It's safe. It's just so full of sediment. It's not exactly pleasant. So this is not in Coyote Gulch itself, but it's very close by. There are also what's called slot canyons. It's a very narrow canyon, sometimes just shoulder width, sometimes even less than that. And they're about 20 or so feet high. So there's the outside. And this is just what it looks like in one of these slot canyons. I'm about 6 feet tall. My hand's another 3 feet or so. So the camera's about 9 or 10 feet in the air off the bottom. So here's one of these slot canyons. And here's another one. So here we are kind of hiking and scrambling through these slot canyons, heading this direction. What's really neat about this one is you can really clearly see the cross-bedding. So here's sand which is tilted this way, and here's sand which is flat from our perspective. So again, these are heavily cross-bedded, wind-blown sand deposits, and it's really, really obvious, especially when your nose is right on it in one of these slot canyons. Okay, so there's your tour of Navajo sandstone in the Southwest. Let's keep marching forward in time. So here we are in the late Jurassic. Again, we just passed the vast desert. The desert has shrunk, and we're returning to a wetter time, as you'll see. Major mountain range building and subduction on the western margin. Lots of erosion and sediment transported towards the northeast. Moving forward in time to the early Cretaceous, a much wetter period, much warmer and wetter climate. And so the green is trying to depict here of much more vegetation. But in terms of geology, it's in Arizona, it's a similar story of compression along the southwestern part of Arizona and erosion and transport of that sediment to the northeast. Here we are in the early Cretaceous. roughly speaking, same story. The big difference is now we have a sea level high period and the formation of the Western Interior Seaway. So we had connection of the Gulf of Mexico to the Arctic Ocean in the north by this shallow sea. And during the late Cretaceous, when this Western Interior Seaway was near its maximum, this is what the world looked like. We had continued mountain building on the southwestern margin of North America, largely erosion and transport of sediment in the northeast direction in northern Arizona. Now, one of the more famous deposits that formed in the Southwest, not so much in Arizona, but more so in Utah and Colorado and New Mexico, is what's called the Mancos Shale. And the Mancos Shale formed along the margins of the Western Interior Seaway as rivers transported sediment from these major mountain regions in the Southwest towards the Northeast, towards the Western Interior Seaway. And the Mancos Shale is famous because of its dark color. It's really rich in oil and natural gas deposits. It's high carbon density shale. And so it's one of these sources of fracking of natural gas and oil that occurs in the western U.S. And so this map down here shows places where the Mancos is outcropped at the surface, this orange, and all the little green dots are oil and gas wells. There's many thousands of them, which are tapping into the Mancos Shale. Okay, so let's move forward in time from the late Cretaceous towards today. So what we have here, we're going to talk again about subduction and uplift of the Rocky Mountains. What we had at this point is subduction of the Farallon Plate towards the northeast. And it was subducting at a relatively normal angle until it started to go flat underneath North America. So the late Cretaceous, this 80 million period or so, when this flat subduction started to occur. And so before then, we had mountain building along the southwestern margin here and the southwestern part of Arizona. But when this flat subduction really got going, volcanism turned off here, and the mountain building really took off earnest in Colorado to this phase. So before, mountain building was all here, but it jumped inward to form the Rocky Mountains of Colorado, northern New Mexico, Wyoming, etc. Okay, so another really important transition in North America is the occurrence of this flat subduction of the Farallon Plate and the evolution of the plate boundary from primarily subduction to primarily transform today. So we've seen this before, but just to jog your memory, we have subduction until now. Transform boundary forms between Pacific North America, and it's growing over time. Transform boundary is getting longer. The subduction zones in the south and the north are getting shorter. One more time. No, we call this the Juan de Fuca now. It's really just the Farallon Plate by a different name. And here's the San Andreas boundary getting longer and longer to today. Now, this also was a period of widespread extension throughout the western U.S., especially in the southern part of Arizona. The Colorado Plateau here has stayed relatively coherent, but extension has occurred all around its margins. So here's a look at the paleogeography here of about 30 million years ago. We're about to transition to the transform boundary. Right now it's all subduction, but right about now, in about 30 million years, is when that corner of the Pacific Plate touches North America, and we have the birth of the San Andreas Fault, which gets longer and longer. So we've already had the uplift of the Rocky Mountains. Now we're about to transition to a transform plate boundary, and the western part of the U.S. is about to start extending roughly east-west. Here we have the birth of the transform boundary. It's about this long now. We go forward in time, it gets longer, and the western U.S. extends roughly to the west. Okay, so the one last thing we need to talk about is on top of these Paleozoic rocks in North America, in northern Arizona, are these relatively young late Cenozoic, late Tertiary volcanic rocks. The pink stuff and the purple and the pink and the orange over here. So Flagstaff is here. These rocks are those that formed as a part of the San Francisco volcanic field. So here's Flagstaff, here's the San Francisco peaks. All these little bumps are one of about 600 individual volcanic features. Most of them are very small cinder cone volcanoes, but at the center of this feature of the volcanic field is the San Francisco peaks, which is an old stratovolcano. Currently, it's the highest peak in Arizona at 12,633 feet. However, there's good evidence to suggest that when it was active, it was significantly taller, between 15 and 16,000 feet, which would have made it the highest mountain in all of the lower 48. Now, we've already spent class talking about the northern Arizona volcanic features, and so I'm not going to say much more about it here. If you're interested, you can go back and take another look at the San Francisco volcanic field virtual field trip from the first part of the course. Okay, so that is the end of my overview of northern Arizona geology. What we're going to do at this point is take a deeper dive into Grand Canyon history, much of which we've talked about before, but we're going to look at some of it in more detail, and then you're going to take a virtual field trip to a location of your choosing in the Grand Canyon. So the next thing to do is just to take a few minutes break and then take a look at Grand Canyon geologic history. The link is here. It's also provided in the D2L announcement for class for today. All right, thanks.